1,400 meters beneath a mountain in Italy, in one of the quietest rooms human beings have ever built, a small crystal of germanium sat in the dark for months, listening. It was listening for the sound of reality making up its mind, a faint glow that matter itself should give off, if gravity is what forces the world to be one thing instead of many. Behind that experiment stands a question physicists have been quietly trained, for nearly a century, never to ask out loud. Physics can predict an electron's behavior to 1 part in a billion. It can simulate colliding black holes. It cannot say a single word about the fact that anyone is home. The Nobel laureate who asked anyway calls it a murky subject and admits he is not sure he should ever have gotten into it. Tonight, the story of the most dangerous question in physics. And by the end, you will know exactly why we stopped asking it. Before we begin, if slow walks along the edges of knowledge are how you like to drift off, a quiet like or subscribe really helps the channel grow. It's a small thing for you, but it means the world to me. Now, let's begin. There is a question that physics is not supposed to ask. It is not written down anywhere as forbidden. There is no rule against it, no committee that bans it, no law on any books. And yet for most of the last 100 years, a young physicist who asked it out loud in the wrong room could feel the temperature drop. Careers have been quietly diminished for asking it. Reputations have been spent on it, the way fortunes are spent on failed expeditions. The question is simple enough that a child can ask it, and most children do, in one form or another, usually at night, usually right around the edge of sleep. The question is this: what is the thing that is doing the understanding? What is consciousness, and where does it live inside the laws of physics? Now, at first, that might sound like a question for philosophers, or for neuroscientists, or for no one at all. But stay with it for a moment, because the question belongs to physics in a way that becomes more uncomfortable the longer you look at it. Physics is, by any honest accounting, the most successful description of reality that human beings have ever produced. Its predictions are not vaguely right. They are right to a precision that is difficult to say out loud without sounding like an exaggeration. The theory that describes how light and electrons interact, quantum electrodynamics, predicts a certain property of the electron, its magnetic moment, and when experimenters measure that property, theory and measurement agree to better than 1 part in a billion. 1 part in a billion is roughly the precision of measuring the distance across an entire continent and getting it right to within the width of a human hair. No religion, no philosophy, no other science has ever made a claim about the world that specific and then watched the world agree that completely. And here is the strange part. Every one of those predictions, every equation, every measurement, every triumphant agreement between theory and experiment was produced by the one phenomenon that appears nowhere in any of the equations: understanding, awareness, the felt experience of grasping a truth. You can search the laws of physics from end to end, from the mechanics of falling apples to the geometry of black holes to the arithmetic of quantum fields, and you will not find a single term, a single variable, a single symbol that stands for the fact that anyone is home. The equations describe a universe of particles and fields in motion, and they describe it flawlessly, and they are silent, completely and eerily silent, about the fact that the universe contains someone to whom the equations mean something. Most of the time, physics simply does not notice this. It is like the old joke about the fish who is asked how the water is, and answers, "What is water?" Consciousness is the water of physics. It is the medium every physicist swims in every working day, the thing that does the calculating and the checking and the understanding. And precisely because it is everywhere in the practice of physics, it is nowhere in the content of physics. A physicist can spend an entire career, a brilliant career, without ever once being professionally required to notice that the theories she manipulates are being manipulated by something the theories cannot describe. But every so often, someone notices. And the ones who notice, and who say so in public, tend to have a difficult time. That is what this story is about. Tonight I want to walk with you through the history of the most dangerous question in physics. I want to show you that there was a time, within living memory, when the greatest physicists alive discussed this question openly, in their books and their letters and their lectures, as a matter of course. I want to show you how the question was then pushed out, not answered but exiled, so thoroughly that a whole generation of physicists was trained to treat it as beneath discussion. And I want to tell you the story of the man, one of the great mathematical physicists of the 20th century, a man who would eventually win the Nobel Prize for work on black holes that nobody disputes, who looked at the exile and decided, more or less alone, to walk the other way. He asked the question. He asked it with more mathematical care than anyone had ever asked it before. He proposed an answer so strange that both physics and neuroscience recoiled from it. He watched an experiment, buried beneath a mountain in Italy, test a piece of his answer, and return a verdict. And near the end of his very long life, when an interviewer asked him what people most misunderstand about him, he named this question, and he said something remarkable. He said it was a murky subject. He said, and this is nearly word for word, that he was not sure he should have gotten into it at all. And then, in the same breath, he said he was glad he did. A Nobel laureate, in his 90s, half regretting the most famous idea of his life, and half unable to let it go. That tension between the regret and the gladness is the emotional center of everything we will explore tonight, because it turns out the question is dangerous in two completely different ways, and by the end of the night you will see both of them clearly. The first danger is the small, human kind. The question has been dangerous to the people who asked it, dangerous to their standing, their funding, their legacies. That danger is a fact of sociology, and we will trace exactly how it came to be, because the story of how a question becomes unaskable is one of the most revealing stories in all of science. The second danger is larger and quieter, and it is the reason the question never actually went away. The question is dangerous to worldviews. Whichever way it is eventually answered, something enormous falls. If consciousness turns out to be nothing but computation, nothing but the shuffling of information according to rules, then something we hold close about ourselves, about the specialness of understanding, about the difference between a mind and a machine, collapses. And if consciousness turns out not to be computation, if there is something the brain does that no rule-following device can ever do, then it is physics itself that has to change, because the physics we have is, almost everywhere you look, a description the rules can run. I promise you this before we go any further. By the end of tonight, you will know exactly why physics stopped asking this question. The answer is not a single villain or a single decree. It is a braid of reasons, some of them respectable, some of them embarrassing, all of them human, and the braid took most of a century to wind. We are going to unwind it slowly, strand by strand, and I am going to hold the full answer back until we have earned it, because the answer only means something once you have seen what the question actually costs. Here is the road ahead, gently. We will begin in the years when the question was still welcome, in the lecture halls and mountain walks of the 1920s and 30s, when the inventors of quantum mechanics, the most successful theory in the history of thought, found to their own discomfort that their theory seemed to have a hole in it, exactly where an observer ought to stand. We will meet the Nobel laureate who dared to say, in print, that consciousness itself might be what closes the hole, and we will watch what happened to him. We will stand in the long silence that followed, the decades when the question went underground, and then we will follow a young mathematics student into a lecture room in Cambridge in the early 1950s, where a theorem about arithmetic, of all things a dry, austere result about what rules can and cannot prove, lit a fuse that would burn quietly for 70 years and lead step by step through black holes and best-selling books and an anesthesiologist's letter and a crystal of germanium under 1,400 meters of rock to the edge of what physics knows about reality. None of this, I should say plainly, will be settled tonight. The question is still open. That is part of what makes it safe to fall asleep to. There is no twist ending waiting to jolt you, no answer that demands you stay awake for it. There is only a long, true story about the strangest gap in our knowledge, told at the pace of a night walk. If you drift off somewhere in the middle, you will drift off inside the same mystery you woke up in this morning, because you have been living inside it your whole life. Every thought you have ever had, including this one, including the slightly dizzy feeling of thinking about thinking, happened in the one place the equations of physics have never been able to reach. So let us begin where the trouble began, nearly a century ago, with a handful of young men in Europe who set out to understand the atom and accidentally built a theory with a hole in the middle of it. They were not mystics. They were the hardest-headed scientists of their generation. And as we are about to see, when their new mechanics finally stood complete in front of them, polished and precise and almost frighteningly successful, several of them looked into it and found, staring back, the very question we have just asked. What they did next, and what it cost, is where our story truly starts. But before we meet them, hold on to one image. Hold on to the fish, swimming in water it cannot see. For the next 2 hours, we are going to try to see the water. And the first people who tried were the ones who built the aquarium. The 1920s were the strangest decade physics has ever lived through. In the space of a few years, a handful of physicists, most of them shockingly young, tore down the picture of reality that had stood since Newton and replaced it with something that worked better than any theory ever had, and made less intuitive sense than any theory ever had. Werner Heisenberg was 23 when he worked out the first version of quantum mechanics on a barren island in the North Sea, where he had gone to escape his hay fever. Paul Dirac was 25 when he found the equation that predicted antimatter. Wolfgang Pauli was 25 when he proposed the exclusion principle that explains why matter is solid. The men building the new physics were young enough that the old guard called their work Knabenphysik, boy physics, and the theory those boys built is, to this day, the most precisely confirmed description of nature in existence. Imagine standing among them for a moment. It is October of 1927, in Brussels, at the 5th Solvay Conference, the most famous gathering of minds in the history of science. 29 people are in attendance, and 17 of them have won or will win the Nobel Prize. The air in the meeting room smells of chalk and pipe tobacco, and coffee gone cold in its cups. At the front, Hendrik Lorentz, courteous and silver-haired, presides in 3 languages. Albert Einstein sits near the middle, quieter than you expect, doodling now and then, waiting. Niels Bohr leans forward whenever anyone speaks, murmuring his agreement or his gentle, relentless objections. Heisenberg and Pauli pass notes like schoolboys. Marie Curie, the only person in the room with Nobel Prizes in 2 different sciences, listens with her chin in her hand. Every morning, Einstein arrives at breakfast with a new thought experiment designed to break the new quantum mechanics, some clever imaginary box of light and clocks that would catch the theory contradicting itself. And every evening, Bohr, having paced and muttered through the day, arrives at dinner with the answer, showing that the theory survives, that it is Einstein's classical intuition, not the mathematics, that has to give. You are watching, in real time, in a hotel dining room, the most fundamental picture of reality humanity has ever held, being stress-tested by the smartest people alive. And underneath every exchange, unspoken but present, sits a question nobody can quite banish. The new theory only gives answers when somebody asks. What, exactly, counts as asking? What is a measurement? What, if anything, is an observer? That question was not a fringe worry, whispered at the edges. It sat at the center of the theory, and the founders knew it. Here is the problem they had built for themselves, and it is worth taking slowly, because the whole night rests on it. Quantum mechanics describes the world with a mathematical object called the wave function. The wave function does not tell you where a particle is. It tells you all the places the particle could be, woven together in a specific, structured blend called a superposition, with a precise weight attached to each possibility. And the equation that governs the wave function, written down by Erwin Schrödinger in 1926, is smooth, deterministic, and continuous. Left to itself, a wave function never chooses. An electron heading toward a screen is, according to the equation, in a blend of arriving here and arriving there, and arriving in 1,000 other places. And the equation is perfectly happy to keep all of those possibilities alive forever, braiding and interfering with one another like ripples on a pond. But that is never what anyone sees. When you actually look, when the electron actually strikes the screen, there is one flash, in one place. The 1,000 possibilities collapse into a single fact, and here is the scandal, the one the textbooks learn to hurry past. Nothing in the Schrödinger equation says that collapse happens. Nothing says when it happens, or how fast, or why, or what exactly triggers it. The founders had to bolt the collapse on by hand, as a separate rule. Rule 1. The wave function evolves smoothly according to the equation. Rule 2. When a measurement occurs, the wave function abruptly abandons the blend and delivers one outcome, with probabilities given by the weights. 2 rules, describing the same world, and the seam between them was hidden inside an innocent-looking word, measurement. The theory never defined it. A measurement was, in practice, whatever a physicist did in a laboratory. The most precise theory in history had, at its foundation, a term whose meaning everyone knew and no one could state. The founders did not shrug at this. That came later, and how it came is the story of our next chapters. The founders worried at it like a loose tooth, and their worrying pushed several of them somewhere modern readers find surprising. They began to write, carefully and in public, about mind. Erwin Schrödinger, whose equation started the trouble, spent his later years writing small, luminous books about exactly this. One of them, published in 1958, is titled Mind and Matter, and in it, and in his earlier book, What is Life, a book that helped inspire the discovery of the structure of DNA, Schrödinger argued that the observer, the experiencing subject, could not simply be deleted from the scientific picture, because the entire scientific picture is, from top to bottom, constructed out of experience. The world we describe with physics, he pointed out, is a world we know only through consciousness, and a science that then declares consciousness unreal has sawed off the branch it is sitting on. Wolfgang Pauli, whose standards were so severe that colleagues called him the conscience of physics, and whose favourite insult for sloppy work was that it was not even wrong, carried on a correspondence for decades with the psychologist Carl Jung, hundreds of letters, trying to work out how mind and matter fit together, convinced that physics and psychology were two views of one underlying reality. The astronomer Arthur Eddington, the man whose eclipse expedition had made Einstein world famous, wrote in 1928 that the stuff of the world is mind stuff, and his fellow astrophysicist, James Jeans, wrote that the universe was beginning to look more like a great thought than a great machine. These were not seance-goers or cranks. These were the working elite of the physical sciences, and their books sold in the hundreds of thousands, because the public could feel what the physicists could feel. The new physics had opened a door, and nobody knew what was on the other side. Then, in 1932, the door got a mathematical frame. John von Neumann, the Hungarian prodigy, who would go on to help design both the modern computer and the mathematics of nuclear strategy, published a book that put quantum mechanics on rigorous foundations, and in it, he traced the measurement problem to its logical end. Suppose, he said, that the measuring device is itself made of atoms, which it is. Then the device obeys the Schrödinger equation too, and when it measures an electron in a blend of two states, the device does not force a choice, it simply joins the blend. The pointer on the dial enters a superposition of pointing left and pointing right. Fine. Add a camera photographing the dial. The camera joins the blend. Add a technician reading the photograph. The technician's eyes, her optic nerves, the neurons of her visual cortex, all of it is made of atoms, and all of it, by the mathematics, simply joins the blend. Von Neumann showed that the chain has no natural stopping point anywhere in the physical world. You can slide the cut between the quantum blend and the single definite outcome anywhere you like along the chain, from the electron to the device, to the camera, to the eye, to the brain, and the predictions come out the same. The mathematics permits the collapse to happen anywhere. It requires it to happen nowhere. Follow the chain of physical systems as far as physics reaches, and the blend never breaks. The first place you are certain the blend has broken, the first link where there is definitely one outcome rather than a weighted mixture of many, is in the last place the chain touches. Experience. Somebody sees the pointer pointing left. Von Neumann himself, the most rigorous man in a rigorous field, noted that the collapse could consistently be placed at the boundary where the physical chain meets the abstract ego of the observer, and some of his readers took that thought entirely seriously. Hold that image for a moment, because it is the hole in the floor of physics that everything tonight grows out of. The most successful theory ever constructed describes a world of blended possibilities, and every time anyone checks, the world presents a single fact, and the chain of physical causes that should explain the transition just keeps passing the responsibility down the line, like a bucket brigade, with no last pair of hands except a mind. The founders saw this clearly. They disagreed about what it meant. They hoped it would dissolve under better analysis, but they did not pretend it was not there. For a couple of decades, roughly from the late 1920s to the 1950s, the question of the observer, and behind it the question of consciousness, was a legitimate, if uneasy, part of physics' conversation with itself. So what happened? How did a question that Schrodinger, Pauli, von Neumann, Eddington, and Einstein's whole generation treated as real become, within one academic lifetime, a question that could quietly end a career? Part of the answer arrived in the person of a shy, precise Hungarian theorist, a close friend of von Neumann's since their school days in Budapest, a man who would win the Nobel Prize for work every physicist admired, and who then did something almost none of them could forgive. He took the argument we just traced and followed it, in print, all the way to its end. His name was Eugene Wigner, and what happened to him, and to the question he carried, is where we go next. Eugene Wigner is not a household name, and that is a small injustice, because the modern world runs on his work. He was born in Budapest in 1902, one of that almost unbelievable cluster of Hungarian geniuses, von Neumann, Szilard, Teller, all from the same few square miles of one city, that their colleagues jokingly called the Martians, because no ordinary planet seemed likely to produce so many of them at once. Wigner brought the mathematics of symmetry into quantum mechanics, and symmetry turned out to be the master key, the recognition that the great laws of physics are statements about what does not change when everything else does, that conservation of energy and momentum and charge flow from symmetries of nature, owes more to Wigner than to almost anyone. He helped design the first nuclear reactors. In 1963, he received the Nobel Prize in Physics. He was, by every account, gentle, formal, almost excessively polite, famous for thanking his laundryman and complimenting the driver who cut him off. Colleagues told a joke about him. Other physicists lose their tempers. Wigner loses his patience politely, once a decade. This mild, meticulous man carried the measurement problem around with him for decades, like a stone in his shoe. He had learned it from the source. He and von Neumann had been friends since their school days, had written papers together in their 20s, and Wigner knew better than anyone what his friend's 1932 analysis actually implied. The chain of measurement has no stopping point in physics. Every physical system that touches the blend joins the blend. The only place the chain visibly ends, the only station on the line where a single definite fact undeniably exists, is conscious experience. And in 1961, at the age of 59, secure in his standing, Wigner did the thing you were not supposed to do. He said it plainly, in writing, under his own name. He published an essay titled Remarks on the Mind-Body Question, and in it he argued that the collapse of the wave function, the transition from many blended possibilities to one actual fact, might occur precisely where von Neumann's chain ends. At consciousness, it was not possible, he wrote, to give a fully consistent description of quantum measurement without reference to the consciousness of the observer. Mind was not a bystander to physics, he suggested. Mind was doing something. Matter blends. Awareness chooses. To make the point vivid, he sharpened a thought experiment that has carried his name ever since, and it is worth feeling from the inside, gently. It came to be called Wigner's Friend, and we need only its outline here, because its real work in our story is what it did to Wigner's own thinking. Wigner imagined a friend inside a sealed laboratory, measuring a quantum system, while Wigner himself waits outside. When did the outcome become definite? When the friend saw it, or only later, when Wigner opened the door and asked? If minds are what break the blend, there is a clean answer. The friend's consciousness settled the matter, and the mathematics that says otherwise stopped applying the moment a mind was involved. Consciousness, in this picture, is not produced by physics. Consciousness is the boundary where physics hands over its report, and something else signs for the delivery. There is a further irony folded into the timing, and it deserves a moment of its own. In 1960, the year before the Mind-Body essay, Wigner had published the piece the wider world remembers him for, a short, luminous meditation titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. In it, he marveled at the miracle, his word, that equations invented by human minds for their own beauty keep turning out to describe the physical world with uncanny accuracy. A gift, he wrote, that we neither understand nor deserve. Read the two essays side by side, written a year apart by the same careful man, and you realize they are the same wonder pointed in opposite directions. One asks why the world so perfectly fits the mind's mathematics. The other asks where the mind sits inside the world the mathematics describes. The first essay became one of the most beloved and cited reflections in all of science, quoted at commencements, engraved in textbooks. The second was received like a stain on the tablecloth. Same author, same pen, same prose style, same theme, the strange kinship of mind and physical law. The field embraced the version that flattered its equations and shunned the version that questioned its completeness. If you want a single clean measurement of the taboo's strength, there it is, a controlled experiment run by history itself. Here is where I want you to slow down and sit with what this actually was. This was a Nobel laureate, one of the architects of modern physics, proposing in a published essay that the mind occupies a special place in physical law. It was the most direct asking of the dangerous question in the 20th century. It was also, very nearly, the last. Because what happened next is the emotional hinge of the whole first half of our story. Nothing dramatic happened. There was no scandal, no formal rebuke, no debate at a great conference where Wigner was refuted before a gasping audience. What happened was quieter and, in its way, colder. The idea was received the way a respectable family receives news of an eccentric relative, politely, briefly, and with a firm change of subject. The essay was cited, categorized, and set on a shelf labeled, in effect, what happens to even the best minds when they wander too far. Physicists who admired everything else Wigner had done learned to mention this one part of his thinking with a small apologetic smile. And Wigner himself, watching all this, did something that tells you more about the danger of the question than any argument could. Slowly, carefully, over the years that followed, he backed away from his own idea. Some of his retreat was for good scientific reasons, and we should be honest about that. Through the 1970s, a German physicist named Dieter Zär, working in his own kind of exile, since his colleagues considered the topic disreputable too, began to develop what became known as decoherence, a rigorous account of how a quantum blend, the moment it touches a warm, busy environment, air molecules, photons, the trillions of tiny interactions every large object is constantly bathed in, gets scrambled so thoroughly and so fast that its parts can no longer interfere with one another. Decoherence showed, with real mathematics, why the world of tables and chairs and laboratory pointers never displays visible quantum blending, with no mind required anywhere in the analysis. It did not, and this matters enormously for everything still to come tonight, actually solve the problem. Decoherence explains why the possibilities stop interfering. It has never explained why only one of them happens. The blend becomes a menu of separate options rather than a smeared wave. But the mathematics still, stubbornly, keeps every option on the menu. The question of who or what places the order remains exactly as unanswered as von Neumann left it. But it moved the mystery far enough from the observer's eye that consciousness no longer seemed forced on anyone, and Wigner, to his genuine credit, took the new work seriously and adjusted. Late in his life he said plainly that his earlier view had put too much weight on consciousness. But some of the retreat, it is fair to say, was not physics. Some of it was weather. It was the felt temperature of a field that had decided, without ever voting on it, that this question marked you. And the truest evidence for that reading comes from a small private moment, decades after the essay, that we know about only because the other person in the room lived long enough to describe it. At Princeton, at a dinner, the aging Wigner found himself in conversation with a younger mathematical physicist from England, a man already famous for his work on black holes, who was quietly nursing his own heresies about minds and physics, and had every reason to ask the older man the obvious question. What Wigner said, according to that younger colleague's memory of the dinner, was disarming. He was not so dogmatic about it as people assumed, he said. Consciousness collapsing the wave function was a view he had played with, and thought possible. That is the phrase that survives. The boldest claim about consciousness in 20th century physics, and its own author, in private, at dinner, describes it the way you might describe a summer you once spent learning the violin. Let that settle for a moment, because it deserves the weight. A man wins the Nobel Prize. He is armored by every honor his profession can give. He follows the mathematics of his best friend, the most rigorous logician of the age, to its logical terminus, and reports what he finds there, once, in careful prose. And the field's response teaches him, gently and without a single formal word, to describe the report, ever after, as play. If you want to know what it costs to ask the most dangerous question in physics, you do not need a dramatic story of a burned heretic. You need only this. The politest man in physics asked it at the height of his powers, and spent the rest of his life softly taking it back. The younger Englishman at that dinner table, by the way, was listening more carefully than Wigner could have known. He disagreed with the older man's answer, as it happens. He had already worked out, with a thought experiment we will meet in its proper place, why consciousness collapsing the wave function had to be wrong. But he did not think the question was play. He thought the question was the weightiest one on the table, and he had begun to suspect that everyone, Wigner included, had been holding it upside down. The collapse does not need the mind, he suspected. The mind needs the collapse. We will spend the whole second half of tonight inside that reversal. But before we can, we have to walk through the silence that made his kind of thinking almost unthinkable. Because between Wigner's essay and that Princeton dinner, something happened to physics as a profession. The door the founders had left open did not just swing shut. It was papered over so smoothly that students stopped believing there had ever been a door. How a living question gets buried without a funeral. That is where we go next. Silences have histories, just as arguments do. The silence that fell over the consciousness question in physics did not fall all at once, and it did not fall for a single reason. It settled the way snow settles, one weightless flake at a time, until one morning the landscape was simply different, and everyone walked on top of the snow as if the ground had always been that shape. It is worth walking through the reasons slowly, because this part of the answer to our title question, why we stopped asking, is the part historians can actually document. Though I will tell you now, so you can rest easy, that it is not the whole answer. The final strand of the braid waits at the end of the night. The first reason was war, and what war did to the profession. The generation that argued about observers at Solvay in 1927 spent the 1940s building radar and the bomb. Physics went into that decade as a small European conversation about the nature of reality. A few hundred people who all knew one another, writing letters about what the wave function means. It came out as a massive, industrialized, largely American enterprise, funded by governments that had seen what physicists could deliver and wanted more of it. The number of physicists exploded. The money flowed toward accelerators, reactors, transistors, rockets, and the culture changed to match the funding. The new physics was a physics of production, of calculable answers to askable questions. A young researcher in 1955, with a family to feed and a security clearance to protect, did not advance his career by wondering in print about the role of the mind in measurement. He advanced it by calculating a cross-section. The philosophical temperament of the founders came to look, to the new generation, like a charming old-world indulgence, like Heisenberg's Plato, and Bohr's endless revisions of a single sentence. There is a phrase that captured the new mood so perfectly that it became the era's unofficial motto, coined later, with affectionate irony, by the physicist David Neumann: shut up and calculate. The theory works, use it. The questions about what it means do not converge, do not publish, do not build anything. Shut up and calculate was never an official doctrine, and that is exactly why it worked so well. Doctrines can be challenged. Moods can only be survived. The second reason was that the mind sciences themselves had locked their own doors. Through the middle of the century, academic psychology in the English-speaking world was dominated by behaviorism, the school that held that science could speak only of stimulus and response, of observable behavior, and that inner experience, being unobservable, was scientifically off-limits, a leftover of folk superstition. Think about what that alliance of silences meant. The physicists would not touch consciousness because it was not physics. The psychologists would not touch consciousness because it was not behavior. The philosophers, who still discussed it, did so in a vocabulary neither science could use. Consciousness became academically homeless, a question with no department, no journal, no conference, and no thesis committee that would let a doctoral student anywhere near it. It is difficult, from where we sit now, to feel how total that homelessness was. For roughly 40 years, from the 1940s into the 1980s, the single most intimate fact of every researcher's existence, the fact that there was something it was like to be them, was a subject on which every serious academic field agreed to have no opinion. The third reason was the quality of the company the question kept. Because the respectable channels were closed, the question flowed into disreputable ones. Quantum mechanics, with its observer-shaped hole, was seized on eagerly by every mystical current of the age. And by the 1970s, the word quantum had become a kind of adhesive for attaching ancient enthusiasms to modern authority. Quantum consciousness, quantum healing, quantum manifestation. The claim that the observer effect proves the mind creates reality, that wanting things quantum mechanically hard enough summons them, that the universe is a catalogue and attention is currency. Let us be plain about this. In fairness to the physicists whose caution we are examining, those claims were false then and are false now. Nothing in quantum mechanics, in any interpretation, in any collapse model, in anything we will discuss tonight, gives your thoughts power over external events. Even the boldest serious proposal ever made, Wigner's own, said only that observation finalizes an outcome among options with fixed probabilities. It never said wishing changes the weights. And the proposal we will spend the rest of the night with runs in precisely the opposite direction. A physical process producing the mind, not the mind commanding the physical. But truth was not the point of the quantum boutique, and its growth had a real cost inside the profession. Every physicist who so much as mentioned consciousness now sounded, to colleagues skimming the title, like the boutique. The cranks did not just embarrass the question, they armed the silence. And the fourth reason, the one with genuine scientific force, is the one we met at the end of the last chapter, decoherence. Through the 70s and 80s, the careful work begun by Dieter Zeh and developed by others showed that you do not need an observer to explain why the everyday world looks definite rather than blended. The environment does the work. A dust grain floating in a sunbeam is struck by so many photons and air molecules each second that any quantum blending of its position is scrambled beyond recovery in a time so short it has no everyday name, a fraction of a second so small that comparing it to the blink of an eye is like comparing the blink of an eye to the age of the universe. The reason you have never seen a coffee cup in two places at once is not that your consciousness forbids it, it is that the universe is noisy, and noise is a relentless interrogator. For most working physicists, this closed the case. The observer-shaped hole had been a mirage. The pointer problem had a mechanism. The question could be retired, not as forbidden, now, but as answered. Except, and here is the turn, the whole night pivots on, it was not answered. It was only relocated. Listen carefully to what decoherence actually delivers, because the fine print matters more than the headline. Decoherence explains why the blended possibilities stop interfering with one another, why the world's options become separate and bookkeepable, like sealed envelopes rather than mingling ripples. It does not, and by its own mathematics cannot, explain why one envelope gets opened and the others vanish. The equations, after decoherence has done all its scrambling, still contain every outcome. The cat, to use Schrödinger's famous prisoner, is no longer in a shimmering blend of alive and dead. It is now in a boring, non-interfering, perfectly well-behaved mathematical sum of alive and dead, and the mathematics has no more idea than it ever did why you, looking in the box, find exactly one cat with exactly one fate. Physicists call this the problem of outcomes, and it is the measurement problem's stubborn, surviving heart. Most of the field stopped looking at it, not because anyone dissolved it, but because decoherence made it possible to do a lifetime of world-class physics without ever meeting it face to face. There is one more piece of unfinished business from the era of the Great Silence, and it is a thought experiment of almost childlike simplicity that quietly demolished the one bold answer anyone had offered. Recall Wigner's proposal. Consciousness collapses the wave function. Matter blends until a mind looks. Now, said a skeptical mathematical mind, take that seriously and buy a ticket to a distant world. Picture an Earth-like planet around some far star, a world of oceans and storms, where life never began. No creatures, no eyes, no minds. Nothing conscious has ever seen its weather, and by Wigner's hypothesis, nothing has ever collapsed it. The planet's atmosphere should therefore remain what the Schrödinger equation says it becomes, an ever-thickening blend of every possible weather, hurricanes overlaid on calm mornings overlaid on snow, a world in a smeared sum of climates. Now send an unmanned space probe past this planet. The probe, being mindless, joins the blend, faithfully photographing the entire superposition of skies. It radios the image home across the light years. The signal arrives on Earth, and a technician glances at the screen. At that instant, and not before, by the hypothesis, the collapse happens. One weather becomes real. And here is the absurdity. It becomes real backwards. The glance would have to settle, retroactively, centuries of that planet's climate, fixing storms that supposedly raged before the probe was launched, before the technician was born. An entire world's history snapped into place by one bored glance at a monitor. The man who devised this scenario drew the only reasonable conclusion, and it is worth quoting his summary in full, because it is 5 words long. It does not make sense. So by the 1980s, the board stood as follows. Consciousness-causing collapse was dead, killed politely by decoherence and absurdity. Consciousness as a research topic was homeless, exiled by physics, banned by psychology, and disgraced by the boutique. The measurement problem was officially considered solved and actually merely anesthetized, its surviving core, the problem of outcomes, dozing behind the word decoherence where hardly anyone looked. The question the founders had asked openly had not been answered. It had been managed, and a whole generation had been trained so well that most of them did not know there had been a question. That is the silence into which our central figure walked, and he walked into it by the least likely door imaginable. Not through the measurement problem at all, through pure mathematics, through a theorem about arithmetic proved in 1931 by a lonely Austrian logician, a result that seems, on its face, to have nothing to do with minds or measurements or the price of asking questions. To find the door, we have to go back in time a little, to a lecture room in Cambridge in the early 1950s, and sit down next to a graduate student who is supposed to be studying something else entirely. Roger Penrose was born in 1931 into a family where brilliance was simply the household climate. His father was a distinguished geneticist who drew impossible figures for amusement. His older brother became a theoretical physicist. His younger brother became a chess champion, 10 times champion of Britain. Dinner table conversation ran to puzzles, geometry, and games invented on the spot. Roger himself drifted first toward mathematics of the purest kind, and in the early 1950s he arrived at Cambridge as a graduate student in algebraic geometry, a field about as far from atoms and consciousness as mathematics reaches, the study of shapes carved out by polynomial equations, beautiful, abstract, and immaculately useless in the best sense of the word. If you had polled his professors, none of them would have predicted that this young geometer would become one of the most consequential physicists of the century, and none of them, not one, could have guessed that he would become the man who reopened the most dangerous question in the field. He was not even studying physics. But he was curious, and Cambridge in the 1950s was a dangerous place to be curious, in the best way. The lecture lists were an open buffet, and a graduate student could simply walk into courses that had nothing to do with his degree. Penrose, by his own account, walked into 3. Remember these 3, because everything that follows tonight, the books, the scandal, the mountain in Italy, all of it grows from this one season of intellectual truancy. The first course was taught by Hermann Bondi on Einstein's general theory of relativity, the physics of curved space and time. The second was taught by Paul Dirac, the same Dirac who had predicted antimatter, on quantum mechanics. Penrose would say ever after that both courses influenced him enormously, and you can trace each one forward like a river. Bondi's course leads, step by step, to the black hole theorems that eventually won Penrose the Nobel Prize. Dirac's course leads to a lifetime of thinking about what the quantum formalism is actually saying. But it is the third course, the least glamorous of the 3, that concerns us tonight. It was a course on mathematical logic, taught by a logician named Steen, and somewhere in that term, the lectures arrived at a result that had been proved 2 decades earlier, in 1931, the same year Penrose was born, by a 25-year-old Austrian named Kurt Godel. The incompleteness theorem. Penrose had heard of it, vaguely. the way one hears of distant scandals. What he had heard was the popular summary that Godel had shown there are things in mathematics that cannot be proved. He remembered not liking the sound of that at all. It sounded like a ceiling, like a sign reading "no entry" posted across some upper floor of mathematics, truths existing that minds are forbidden to reach. And then he sat in the lectures and learned what the theorem actually says, and the effect on him, by his own testimony, was not disappointment. It was closer to revelation. He found it, in his word, stunning. To see why, we should sit where he sat. Let me take you there for a moment. It is a grey Cambridge afternoon in the early 1950s, in a lecture room that smells of chalk and damp wool and the cold tea of the English term. Rain ticks against tall windows. The lecturer, precise and unhurried, is doing something on the blackboard that looks, at first, like a parlour trick. He is building a sentence of pure arithmetic, a statement about whole numbers, nothing more, but he is building it with mirrors. Through an ingenious coding invented by Godel, every statement about numbers can itself be given a number, so that arithmetic becomes capable of talking about arithmetic. Sentences acquire code numbers the way houses acquire addresses, and provability itself, the property of being derivable from the rules, becomes a matter of arithmetic relations between addresses. The lecturer writes, and the young geometer in the audience leans forward, because he can see where this is going before it arrives, and he can hardly believe the destination is allowed. The sentence taking shape on the board is engineered to say something about its own address. It says, when you unwind the coding, exactly this. I am not provable by these rules. The chalk stops. The room is quiet in the way rooms are quiet when something irreversible has just been done politely. Consider, says the lecturer, what this sentence can and cannot be. Suppose it is false. Then, since it says it is unprovable, it would be provable, and the rules would be proving a falsehood. If your rules prove falsehoods, they are broken, worthless, and every theorem they have ever given you is suspect. So if the rules are sound, the sentence cannot be false. It must be true. True, and therefore, by what it says of itself, unprovable. There it stands on the blackboard, in front of a room of damp students on an ordinary afternoon. A statement of arithmetic that is true, and that the rules, however long they run, however cleverly they are applied, can never reach. It is worth pausing over the man who built that sentence, because his shadow lies across the whole rest of our story. Kurt Gödel proved the incompleteness theorem in Vienna in 1931, at the age of 25, and the world he detonated it inside was not a casual one. The greatest mathematician of the age, David Hilbert, had spent decades organizing a grand program to place all of mathematics on complete and certain foundations, to show that the rules, sufficiently well chosen, could in principle settle every mathematical question, that in mathematics there is no ignorance that cannot be worked off. We must know, Hilbert had declared. We will know. The words were engraved, in the end, on his tombstone. Gödel's paper, quiet, technical, and 20-some pages long, ended the program in its strong form forever. No consistent rulebook, rich enough for arithmetic, can settle every question. Not because mathematicians are not clever enough, but because rulebooks, as such, have a blind spot built into their very nature, and the blind spot can be constructed, exhibited, and pointed at. Godel himself was the strangest of messengers, precise to the point of fragility, so cautious that he published reluctantly and qualified everything, a man who would later, in his American years at Princeton, become Einstein's closest walking companion. Einstein said in his last years that he went to his office chiefly for the privilege of walking home with Godel. The two of them, the man who unseated absolute time and the man who unseated absolute proof, strolling under the New Jersey trees, arguing gently about what was left standing. And one more detail, almost too fitting to be true, but true. Godel took his own theorem to imply, as a strict logical alternative, that either the human mind surpasses every machine, or there exist truths forever beyond human reach. And he privately found the second option implausible. The man who built the sentence suspected what the young geometer in the damp lecture room was about to suspect. The theorem was not a ceiling, it was a mirror, and something in it was looking back. Now, the young Penrose sits back, and the thought that will define the second half of his life arrives, not as a suspicion, but with the force of a proof. Something has just happened in this room that needs explaining. Every student present, following the argument, has come to know that the Godel sentence is true, known it with mathematical certainty, but the rules cannot prove it, so the knowing did not come from the rules. Where did it come from? Trace it honestly. You believe the sentence is true because you believe the rules are sound, that they prove only truths. And why do you believe the rules are sound? Not because the rules say so. A broken system can happily certify itself all day long. Godel himself proved, as a companion result, that no consistent system of this kind can ever establish its own consistency. Your trust in the rules comes from outside the rules. It comes from understanding what the rules mean, from seeing that this axiom is obviously true of numbers, that this inference obviously preserves truth. Meaning, seeing, understanding, and here is the point Penrose could not get past, then or ever. That act of understanding, the thing every student in the room just did, is precisely what no rule-following procedure can fully capture. Because for any fixed system of rules you propose as the complete mechanism of mathematical understanding, Godel's recipe manufactures a sentence that the rules cannot prove, and that understanding, standing outside the rules and trusting them, can see to be true. Whatever understanding is, it always has this one strange inch of reach beyond any rulebook you try to lock it inside. Penrose would spend decades refining that argument, and tonight we will meet both its power and its critics, who are serious and numerous. But in the lecture room, in the 1950s, what mattered was the shape of the thought, and I want you to hold its shape the way he held it, because it is the seed crystal of our whole story. Rules can compute, rules cannot understand, and understanding, whatever it is something brains do while being, presumably, physical objects obeying physical law. The young man gathering his notes as the rain lets up is not yet asking the dangerous question. He is a geometer. He has a thesis to write. The insight goes into a pocket, the way insights do, and it stays there through an entire glittering career, through the 1960s, when his theorems about collapsing stars remake our understanding of black holes, through honors and professorships, 20 years and more. But pocketed is not forgotten. A thought like that ticks, because look at what it quietly implies, and feel the fuse begin to burn. If understanding is something the brain does, and understanding is not computation, then somewhere in the physics of the brain, and therefore somewhere in physics itself, there must be something that is not computation. Some process no algorithm can imitate, and the physics Penrose knew, the physics he was teaching and extending, the physics of Bondi's course and Dirac's course, was computable through and through. Every law of it could, in principle, run on a machine. Almost every law. There was one exception, one place in all of known physics where the mathematics goes strange. One door left unlocked, and it was the very door the founders had argued over at Solvay, and the profession had spent 30 years papering shut. Before we can walk through that door with him, we need to do what Penrose did and take the argument about rules and understanding seriously enough to test it, because if it fails, the whole night's journey ends here. Does the sentence on the blackboard really prove that minds outrun machines? That is where we go next. Every argument that matters has a moment when it must leave the safety of its birthplace and survive in the open. The thought Penrose carried out of that Cambridge lecture room, that understanding cannot be computation, is one of the most contested arguments of the last 100 years, and before we follow it into physics, we owe it, and ourselves, an honest stress test. So let us lay it out in the open air. plainly, and then let its critics take their best swings. This is the part of the night where we slow down and think together. No scenery, no history, just the argument itself, turned over in the hands like a stone. The argument runs like this. Suppose that human mathematical understanding is, at bottom, a computation, not metaphorically, but literally, that there exists some definite system of rules, some algorithm, however enormous, that captures everything human mathematicians can do when they understand and verify mathematics. That algorithm might be the wiring of the brain, as shaped by genes and learning, the sum total of our mathematical instincts and training. Now apply Godel. If we knew this rulebook and trusted it to be sound, then Godel's recipe would hand us a specific arithmetic sentence, the rulebook's own confession, in effect saying, "I am not provable by these rules." And, exactly as in the lecture room, by understanding the construction and trusting the rulebook's soundness, we would come to know that this sentence is true. But knowing it is precisely what the rulebook cannot do. So we would be doing something the algorithm that allegedly constitutes us cannot do, and the supposition collapses on itself. Conclusion. Human understanding is not the running of any knowable, trusted rulebook. Whatever grasps truth is not, in the final analysis, an algorithm. Penrose did not invent this reading from nothing. The philosopher John Lucas had pressed a version of it in 1961, the very year of Wigner's essay, As It Happens. And even Godel himself, cautious as a locksmith, had remarked that his theorem seemed to imply a disjunction, that either the human mind surpasses every machine, or there exist mathematical truths absolutely beyond human reach, and he found the second option hard to believe. Now the critics, and they deserve their full turn at the stone, because they include some of the sharpest logicians and philosophers of the era, Hilary Putnam among the first and fiercest, Solomon Pfefferman among the most careful, and a long line of computer scientists since. Their central reply has real teeth, and here it is. The argument, they say, smuggles in an assumption exactly where it can least afford one. It assumes that we know we are consistent, that our mathematical rulebook is sound. But do we? Human mathematicians make errors constantly. Whole eras of mathematics have harbored contradictions that took generations to surface. Perhaps we are an algorithm, but a messy, inconsistent, error-prone one, and Godel's theorem simply does not apply, because it speaks only of consistent systems. Or perhaps we are a consistent algorithm, but one so tangled, so gigantic, forged by evolution rather than design, that we can never actually know our own rulebook, never write it down, never perform the Godel construction on ourselves. In that case, the magic sentence exists, but we can never build it, never see its truth, and no contradiction ever arises. Notice how strange and interesting this defense is. To save the claim that the mind is a machine, the defenders must insist that it is a machine that can never understand itself, a program forbidden, on pain of paradox, from reading its own listing. The mind is a computer, they say, but necessarily an unknowable one. Penrose answered at book length, twice, tightening the argument, and the critics answered the answers, and the honest summary, which I give you without embarrassment, is that after 60 years the matter stands unresolved. This is not a proof with a whole that everyone can point to. It is a standoff about what we may assume about ourselves, and it has stayed a standoff because both sides are defending something enormous, and it is worth pausing, as we let the argument rest, to notice exactly what each side is defending, because this is where the night's opening promise begins to cash out. If the critics are right, then understanding, the click you felt in the lecture room scene, the moment a truth becomes yours, is what a sufficiently complicated rulebook feels like from the inside, and nothing more. Every insight you have ever had was a derivation. If Penrose is right, then every computer ever built, and every computer that ever will be built, in the sense we currently mean by the word, a device executing rules, is permanently on the far side of a wall from you. It can be trained on every book ever written. It can produce, flawlessly, the outward behavior of comprehension. And there will be, on this view, nobody home. Not because its makers were clumsy, but because rule-following is simply not the kind of thing that understanding is. Penrose, characteristically, did not soften this for the age that was arriving. The term artificial intelligence, he remarked in that same late interview, is a misnomer. It may be artificial cleverness, he said, but it does not involve any understanding. You are just following the rules. Whatever you make of that as a claim, notice what it is not. It is not a claim that machines are weak. It is a claim that cleverness and understanding are two different substances, and that we have gotten spectacularly good at manufacturing one, while having no idea, none at all, how nature manufactures the other. Every time you ask a machine a question and receive a fluent answer, you are performing, whether you mean to or not, a small experiment on the most dangerous question in physics. There is one more feature of the argument to notice before we move, and it is the feature that makes the rest of tonight possible. Look at the argument's shape. It is entirely negative. It says understanding is not computation. It does not say one word about what understanding is. It is a signpost pointing away from every computer ever imagined, standing at the edge of a fog. Most people who accept an argument like that would stop at the signpost. It takes a particular kind of mind, a mind trained to believe that every real phenomenon must live somewhere in physical law, to read the signpost and start walking into the fog. And this is where Penrose parts company, decisively, from every mystic who ever borrowed the word quantum. Because there is a cheap exit here, and he refused it. The cheap exit is dualism, the declaration that mind is simply outside physics, a second kind of stuff, a ghost that mathematics cannot bind. Say that, and the argument is over, and so is the science. Penrose said the opposite, and said it flatly, in that same interview, in words worth carrying with you through everything that follows. I am a physicalist, he said. Whatever is going on in our heads is following the laws of physics. Hold those two commitments side by side and feel how they grind against each other, because that grinding is the engine of the entire second half of our story. Commitment 1. Understanding is not computation. No rulebook does what minds do. Commitment 2. Minds are physical. Brains obey the laws of physics and nothing else. There is exactly one way both commitments can be true at once. Somewhere inside the laws of physics themselves, there must be something that is not a computation, some genuine physical process that no algorithm, however large, can fully simulate. The laws we teach, the laws that run the planets and the transistors, would have to contain, hidden somewhere in their machinery, one component that does not run on rules. Put that way, it sounds almost hopeless, because everything about physics feels like rules. And so Penrose did the natural thing for a mathematician of his temperament. He went through the laws of physics one by one, the entire inventory of reality's known machinery, asking a single question of each. Can a computer run you, in principle, to any desired accuracy? It is one of the strangest audits ever conducted, a census of everything that happens, searching for the one thing that might not be clockwork. And I will tell you now, so you can listen to the next part of the night with the right kind of attention, that the audit comes back almost completely empty. Law after law, force after force, from the fall of an apple to the shudder of colliding black holes, the answer keeps coming back, yes, computable. Yes, computable. Yes. Almost everywhere. In all of known physics, there is exactly one process that fails the test. One place where the mathematics itself refuses to be an algorithm. You already know, from the first half of tonight, where the trail is heading, and part of the pleasure now is watching the two halves of our story, the exiled question of the founders and the pocketed insight of the geometer, curve slowly toward each other across 30 years, like two rivers that have no idea they share a sea. The audit is where we go next. An audit of reality sounds like an impossible undertaking, but physics is more compact than it looks from outside. The whole known machinery of the universe, everything from the drift of continents to the shine of stars to the chemistry of your blood, runs on a remarkably short list of fundamental laws, short enough to walk through in an evening, short enough that Penrose could take them one at a time and ask his auditor's question. Can a machine run you? Is there anything in you, even in principle, that a step-by-step procedure could not imitate to any accuracy we choose? Come along on the walk. It is one of the quietest and strangest journeys in this whole story, and the scenery is everything that exists. Begin with Newton, classical mechanics, the physics of pushes and pulls, of orbits and pendulums and cannonballs, the physics that ran the world's imagination for 2 centuries. Newton's laws are differential equations, which is to say, recipes. They tell you, given where everything is now and how it is moving, exactly what happens next. Feed the recipe to a computer, let it take small step after small step, and the machine will march the solar system forward for you across 1,000,000 years. The predictions may become impractical when systems turn chaotic, when tiny errors compound, but impractical is not the same as non-computable. Chaos makes forecasting expensive. It never makes the underlying process anything other than rule following. The auditor's stamp comes down, computable. Next, Maxwell. In the 1860s, James Clerk Maxwell wrote down 4 equations that unified electricity, magnetism, and light. 3 apparently different phenomena revealed as one thing seen from 3 angles. Every radio wave, every glint on water, every nerve impulse in the hand holding your phone rides on Maxwell's mathematics. And Maxwell's equations are, again, recipes, field values evolving step by step across space and time. Engineers simulate them every working day, in antenna design, in fiber optics, in the layout of the chip you may be listening to me on. Computable. Now Einstein, both movements. Special relativity, from 1905, rewrote space and time into a single 4-dimensional fabric, but its mathematics is if anything cleaner than Newton's, and machines handle it without complaint. General relativity, from 1915, is harder, famously harder, the curvature of space and time feeding back on the matter that curves it. Equations so tangled that for decades, exact solutions could be counted on your fingers. For a while, one might have wondered whether such a theory could be computed at all. The wondering is over. There is now an entire discipline called numerical relativity, whose practitioners simulate, on supercomputers, the most violent events in nature, 2 black holes spiraling together, tearing at the geometry of space, merging into one. When gravitational wave detectors finally heard such a collision, in the 2010s, the observed ripple was matched against enormous banks of simulated waveforms, computed general relativity, and the match was exquisite. Penrose, in that late interview, tipped his hat to exactly this work. People do great things with computers on colliding black holes, he said. It is pretty impressive. Note the shape of the compliment. The wildest, most non-linear theory in classical physics, the theory of warped time itself, submits, in the end, to step-by-step arithmetic. Computable. So classical physics, all of it, everything before the quantum, passes the audit as clockwork. Beautiful, chaotic, relativistic clockwork, but clockwork. If understanding is not computation, understanding is not hiding anywhere in the classical world. Which brings the walk to the quantum, and here, you might think, the story must surely change. Quantum mechanics, the theory of blur and chance, of particles that take every path, of Schrödinger's poor cat. Surely here the clockwork breaks. And here the audit delivers its first surprise, one that separates people who have heard about quantum mechanics from people who have looked at its gears. The famous Schrödinger equation, the beating heart of the theory, the law that evolves the wave function, is not wild at all. It is linear, smooth, and utterly deterministic. Given the wave function now, the equation delivers the wave function later, exactly, uniquely, no dice anywhere. All the blur lives inside the object being evolved. The evolution itself is as orderly as a train schedule. Chemists simulate it to design molecules. Engineers simulate it to design the very quantum computers we keep hearing about. The state may be too large to handle in practice for big systems. Penrose himself waved at this. Maybe lots of variables, he said. But still, it is the same sort of thing. In principle, step-by-step procedure. The auditor, a little unnerved now, stamps again. Computable. And so the walk arrives at the last door. Because as you and I already know, the Schrodinger equation is only rule 1 of quantum mechanics. There is a rule 2, measurement, collapse. The moment when the smoothly evolving blend of possibilities abruptly becomes one actual fact. When the electron that was everywhere on the screen is suddenly a single flash. This is the process the founders could not define, the process von Neumann chased down his endless chain, the process Wigner pinned on consciousness, and the field pinned on nothing at all. Set aside, for tonight's purposes, the interpretive wars we visited earlier. Look at collapse only through the auditor's lens, and ask the one question of it. Is it computable? And the honest answer of standard physics is astonishing when you finally hear it plainly. Standard physics does not compute the collapse. It cannot. It does not even try. What the textbook provides is a probability rule, the Born rule. It tells you the odds of each outcome, and the odds are computable, beautifully computable. But the outcome itself, which possibility actually becomes fact in this particular run of the experiment, is delivered by nothing in the theory. It is called random, and the word random, when you press on it, is not a mechanism. It is a confession. It says, no rule known to us produces this result. Every other process in the audit, we could hand to a machine and say, do what nature does. Collapse we cannot. The best a machine can do is what casinos do, generate pseudo-random choices and mimic the statistics. The statistics, yes. The individual event, no. Here, and only here, in the entire inventory of physical law, the clockwork picture simply runs out. Now, most physicists, and let us give their view its full weight, read this as randomness and nothing more. Nature flips coins at the bottom. The coin flips obey the computed odds, and there is nothing further to explain, no hidden machinery, no further account, and certainly nothing to do with minds. That is a perfectly coherent reading, and it is the majority one. But watch Penrose at the last door, because this is the hinge of his whole edifice, the sentence on which the second half of tonight turns. That randomness, he said, I would argue, is an approximation. There is something going on which is not just explained by randomness. Feel what he is proposing. Where the textbook writes random and closes the book, he suspects a process, a real, physical, lawful process that selects outcomes. A process whose statistics look like coin flips from the outside, the way the weather looks like coin flips if all you keep is a rain diary, but which has, underneath, its own strange dynamics. And here is the crucial move, since everything else in physics passed the audit, since collapse is the only door left unlocked, then if the brain does something non-computational, this is the only place in known physical law it could possibly come from. The Godel argument says understanding outruns every rulebook. The audit says all of physics is rulebook except one process. Put together, the conclusion is almost forced, and it is unlike anything in the history of the question. Whatever consciousness is, Penrose concluded, it depends on the collapse of the wave function. Not consciousness causing collapse. Wigner's doomed arrow, killed by the lifeless planet. The arrow reversed. Collapse. The objective, physical, choosing of realities, happening everywhere, always, in every rock and raindrop, mindlessly, and the brain, alone among objects we know, having somehow evolved a way to harness that process, to orchestrate it, to build understanding out of the one ingredient in the universe that is not clockwork. I know that is a lot to take in, and we are going to take it slowly because we have the whole rest of the night. But before we go further, notice what the audit has quietly done to our story. It has taken the founder's embarrassment, the measurement problem, the crack in quantum mechanics that the profession spent decades painting over, and revealed it as the only possible home for the mind. The exiled question and the pocketed insight have met, exactly where two rivers meet, at the lowest point in the landscape. Everything now depends on what collapse actually is. If it is going to bear this much weight, it cannot remain a word in a textbook. It needs a mechanism, a trigger, a timescale. It needs, in short, to become physics. And to get there, we first need to understand what kind of reality a quantum superposition actually has, which turns out to be one of the most delicate questions ever asked. Delicate enough that Einstein himself had to invent the standard for answering it. Let me show you, with a coffee cup and an electron, the two kinds of reality this universe seems to run on. Penrose has a way of explaining the two kinds of reality that is so homely, so disarmingly literal, that it sneaks past your defenses before you notice it has rearranged your world. He did it in that late interview with the coffee cup sitting in front of him, and I want to do it with you now, slowly. Because once you feel this distinction in your hands, everything that remains tonight, the gravity, the microtubules, the mountain, follows almost naturally. So settle in and let us interrogate two witnesses, a cup and an electron. Begin with the cup. Picture it within reach, a plain ceramic cup, still warm. Penrose's suggestion is that you ask it a question, and he even supplies the wording. "Hello, cup," he says. "What is your shape?" And the lovely thing is that the cup, in every way that matters, answers. Run your eye around it, and the cup reports, without hesitation, "I am more or less a circle at the top. I have this particular curve down the side. I am symmetric all the way around, apart from the handle." Ask it anything else in its competence. Where are you? Here, on the table, entirely. How warm are you? This warm, everywhere, at once. The cup is not shy. The cup holds a full press conference on the subject of itself, continuously, for any questioner, and every answer is definite, and all the answers agree with one another, and asking costs the cup nothing. It is not changed by your curiosity. This is classical reality, the reality of every object you have ever touched, and its signature is exactly this cheerful answerability. Things have properties. The properties are there whether or not anyone asks. Questions merely read off what already exists. Your entire life, every room you have slept in, every face you have loved, has been furnished exclusively with things like the cup. No wonder we mistake its manners for the manners of the universe. Now the second witness. Shrink down, in your mind's eye, past the cup's glaze, past its molecules, down to a single electron, and consider one of its properties, its spin, a kind of intrinsic turning that every electron carries. And now, politely, ask, "Hello, particle, which way are you spinning?" And here, Penrose says, and you can hear the smile in the physics, the witness goes strange. The electron looks at you blankly, he says, and replies, "I do not answer questions like that. It is not being coy. It is telling you the truth about its own kind of existence." The electron does not have an answer to your open question, not a hidden one, not a shy one. There is no fact of the matter, sitting inside it, about which way it points. What you can do, and this is the strangeness, is suggest a direction. You may say, "Are you spinning this way, along the line I am now choosing?" And to that question, the electron will always answer yes or no on the spot. But watch the pattern of its answers, because this witness has rules of its own. If, unknown to you, the electron was prepared pointing exactly the way you guessed, it says yes, every time, with certainty. If you guessed exactly backwards, it says no every time. And if you guessed somewhere in between, it answers yes sometimes and no sometimes, with odds that depend, precisely and computably, on the angle between your guess and its preparation. The answers exist only in response to questions. The questions themselves disturb the witness, and yet the pattern of responses is lawful to the last decimal place. That is quantum reality. It is not less real than the cup. It is differently real, real in the way a possibility is real, structured, exact, and unwilling to pretend it is furniture. And lest that sound like a metaphor or a philosopher's fancy, let me put real laboratory flesh on it, because the electron's strange manners are among the most thoroughly documented facts in science. The interrogation I just described is performed, in essence, every day in apparatus descended from a 1922 experiment in which silver atoms were sent through a shaped magnetic field, a field that functions exactly as our polite question does. Which way are you spinning along this line I have chosen? The atoms are never permitted a vague answer. Every single one lands in one of exactly two spots, yes or no, this way or that, and the statistics across thousands of atoms follow the angle rule to the decimal. Physicists have asked the question of electrons, of atoms, of photons, in laboratories on every continent, for 100 years, and the witness has never once broken character. It never volunteers, it never elaborates, it answers only the question asked, and it forgets, in a precise and testable sense, every answer it gave before. If a courtroom witness behaved this way, we would call it evasion. In the quantum world, it is simply citizenship. The rules of the second reality are not lax versions of the first reality's rules. They are a different constitution altogether. You might reasonably ask how physicists can call something real when it refuses to hold properties before being asked. Einstein asked exactly that, and his answer became the field's gold standard, so let us take it from him. Real, said Einstein, in a criterion he laid down in a famous 1935 paper, is anything whose value you can predict with certainty, without disturbing the system. The electron prepared along a known direction meets that standard, in that one direction. Ask it the question it was prepared for, and yes arrives with certainty, no disturbance, no gamble. By Einstein's own rule, something is really there, but only that one question has a guaranteed answer. Every other question gets odds. So the electron's reality is a strange, partial, directional kind of being. Certainty down one line of questioning, chance down all others. Penrose takes Einstein's criterion and turns it into the definition of the second kind of reality. Classical reality answers every question. Quantum reality guarantees one and gambles the rest. Two manners of existing in one universe, and every object in creation belongs to one family or the other, except that sentence, as you already suspect, is not quite right. And in the not quite lives everything. Because the central teaching of quantum mechanics, the one confirmed in laboratory after laboratory for a century, is that the cup is made of electrons. The answerable is built from the unanswerable. There is no wall in nature with quantum things on one side and classical things on the other. No dotted line where the strangeness signs a treaty and agrees to stop. The mathematics is perfectly happy, remember von Neumann's chain, to write a wave function for two atoms, or 2000, or a dust grain, or a cup, and superpositions of large objects are not forbidden. They have been built. Physicists have put molecules of many hundreds of atoms through interference experiments, and the current records, set in Vienna, involve custom-built molecules of roughly 2,000 atoms, tens of thousands of times the mass of a hydrogen atom, objects big enough to be almost dust, and the molecules behaved like the electron, taking blended paths, refusing the question which way did you go. Each year the experimenters build the blend a little bigger, and each year it holds. There are serious, funded proposals to do the same one day with viruses, and nothing in the mathematics says they will fail. The blend is not a story about small things. It is a story about undisturbed things, and small things are merely easier to keep undisturbed. So the real question, the one our whole night now funnels into, is not why is the electron strange? The electron is allowed to be strange. The question is the cup. Why does the cup always answer? What, precisely, forces every large object in the universe to hold its press conference, when the laws that govern its every particle would permit it to go blank-faced and refuse, like its constituents do? You have heard the mainstream reply already: decoherence, the environment, noise as the relentless interrogator. And you have heard the fine print, that decoherence silences the interference but never chooses the outcome. Now feel the question the way Penrose feels it. Somewhere between the electron and the cup, refusal turns into answerability. Blend becomes fact. Not approximately, not for practical purposes, but actually, every single time, everywhere in the universe, in the heart of stars, and in interstellar dust clouds, where no environment worth the name exists. Wherever matter gathers in sufficient amount, the quantum manner of being gives way to the classical. Something does that. Some process, real and physical and universal, closes the press conference gap. And whatever that process is, it is rule 2. It is the collapse. It is the one entry in the audit of physics that came back stamped not computable. The one door, in all of natural law, behind which a non-algorithmic mind could live. So the search has a shape now, and feel how sharp it has become. We are no longer asking the founder's foggy question, what is a measurement? We are asking an engineer's question. What physical variable decides when a superposition dies? What does the executioner read? Mass, size, complexity, time, what, and where is the threshold, and can we calculate it, and can we test it? The moment you ask it that way, one candidate steps forward, so quietly that for decades almost nobody heard it. Because there is one force in physics that has been standing in the corner of this entire story, unmentioned all night, a force that cares about exactly the thing that separates electrons from cups. Not their charge, not their speed, their mass. The force that holds your blankets to the bed, and the air to the planet, and the planet to its star. The gentlest force in the universe, and the only one that every particle of the cup contributes to, and the one force that quantum mechanics, after a century of trying, has never been able to swallow. Gravity. What if gravity is the executioner? What if the same force that folds space-time around black holes is what closes every press conference, what turns blend into fact, what makes the world definite enough to sleep in? That is the proposal at the very center of tonight, the strangest and most beautiful idea in this whole story, and it comes with something none of its rivals ever had: a number, a testable, calculable number. Let us go and meet it. Gravity is the misfit of modern physics, and its misfit status is exactly what qualifies it for the role we are about to consider. Every other force in nature, electromagnetism, the strong force that binds nuclei, the weak force that governs certain decays, has been fully translated into quantum language. Each has its quantum field, its messenger particles, its computable rules, all of it verified to spectacular precision. Gravity alone has refused the translation. After a century of effort by the smartest people alive, there is still no accepted quantum theory of gravity, and the refusal is not a detail. According to Einstein, gravity is not really a force at all. It is the shape of space-time itself, the sag and curve of the stage on which all the other actors perform. To quantize gravity is to quantize the stage, and nobody knows how to do it. Now watch what happens when you push the two great theories of the 20th century into the same room and ask the simplest possible question. Quantum mechanics says objects can exist in superpositions of two places. General relativity says every object bends space-time around itself. So, take a single small mass and put it in a quantum blend of being here and being there. Where does space-time sag? Feel the dilemma close, like a trap. If the mass is in a blend of two locations, then the geometry of space-time must be in a blend of two shapes, a superposition not of a particle, but of two universes worth of stage, each with its dent in a different place. Quantum mechanics is formally content with that. Einstein's theory finds it close to meaningless, because the two geometries do not even share a common definition of time against which the blend could smoothly evolve. This collision, mass in superposition versus space-time with one shape, is arguably the exact point where the two pillars of physics grind against each other, and it is here, in the grinding, that Penrose located his mechanism. His proposal, radical and conservative at once, is this: nature resolves the conflict by refusing to sustain it. A superposition of two mass distributions is also a superposition of two space-time geometries, and superposed geometries are unstable. They cannot last. The blend decays, spontaneously, objectively, with no observer anywhere in the story, into one geometry or the other. That decay, says Penrose, is the collapse of the wave function. Rule 2 is not a footnote about measurement. It is gravity, doing quietly and constantly what it has done all along, insisting that the universe have a definite shape. And here is where the idea earns its place in physics rather than philosophy. It makes a number. Penrose realized you can calculate how unstable a given superposition is, using nothing but quantities physics already owns, and the recipe is simple enough to describe in words on a sleepy night. Take the two candidate locations of your object, here and there. Ask, how much gravitational energy would it cost to pull two copies of this object apart, from perfect overlap to that separation? That energy, the gravitational self-energy of the difference between the two arrangements, measures how badly the two space-time geometries disagree with each other. Call it the separation cost. Then the rule is one line. The lifetime of the superposition is a fundamental constant of nature, Planck's constant, divided by that separation cost. Big disagreement, brief life. Tiny disagreement, almost eternal life. That is the whole theory. And before we taste its consequences, one act of intellectual honesty that tells you a great deal about the man. Penrose learned, after developing the idea, that a Hungarian physicist named Lajos Diosi had arrived at essentially the same lifetime formula, independently, about 2 years earlier, in the late 1980s, working in relative obscurity in Budapest. Penrose has insisted ever since on sharing the credit. You can call it the Diosi lifetime, he said. I sometimes call it that, and the proposal is known today as the Diosi-Penrose model. Two people, unknown to each other, one from the mathematics of black holes, one from the theory of measurement, converging on the same formula, is either a coincidence or a hint, and physics has learned to pay attention to that kind of hint. Now run the numbers through the world, because this is where the proposal becomes almost indecently satisfying. Start with the cup, in a hypothetical blend of sitting here and sitting one hand width to the left. The separation cost for an object of that mass, moved that far, is by everyday standards minuscule. Gravity is feeble, but Planck's constant, the numerator, is so fantastically small, a decimal point followed by 33 zeros before the digits begin, that the division comes out brutal. The lifetime of the cup's blend is a sliver of a second, so thin that no clock ever built or imagined could resolve it. In Penrose's words, absolutely instantaneous. The cup cannot hold two positions long enough for the universe to notice it trying. It answers every question, because gravity forecloses, at once and forever, its right to remain blank. Now shrink the object. A dust grain's blend lasts longer. A large molecule's, longer still. An electron, whose mass is so slight that its separation cost is nearly nothing, can float in superposition, by this arithmetic, for longer than the age of the universe. Maybe take a long time, said Penrose of the small things. Depends how big it is. Do you see what the formula has done? It has drawn, with one line of algebra, the exact border we went hunting for at the end of the last chapter, the border between the electron's blank-faced refusal and the cup's cheerful press conference. Below the line, quantum manners. Above it, classical facts. Not because minds watch, not because environments interrogate, but because mass bends space-time, and space-time will not stay two shapes for long. The most familiar mystery in the world, why the furniture of life is reliably here rather than blurred, gets an answer with units on it. The world looks classical because the world is heavy. And notice, before we rest inside this picture, how strange it is that gravity, of all forces, should be the one holding the pen. Gravity is famously, almost comically, the weakest player in physics. The electromagnetic force between two protons is stronger than their gravitational attraction by a factor of about 10, followed by 35 zeros. A toy magnet lifts a paperclip against the pull of the entire planet. For nearly every purpose in atomic and molecular physics, gravity is not merely negligible, it is unmentioned, dropped from the equations without apology on page 1. And yet in this proposal, the negligible force holds the decisive office. The reason is that gravity has the one credential none of the stronger forces can claim. It is universal. Electric charges cancel, positive against negative, and most matter is neutral. The nuclear forces reach barely beyond the nucleus itself, but every particle of the cup, every proton, neutron, and electron contributes its mass to the bending of space-time, always, without exception, and the contributions never cancel, only accumulate. Gravity is weak, but it is the only force that counts everyone. It grows without limit as matter gathers, which is exactly the property an executioner of superpositions needs, blind to charge and chemistry, indifferent to detail, sensitive only to the one thing that separates the cup from the electron, amount. The feeblest force in nature turns out to be the only one positioned, at every scale, everywhere, to enforce the border between the two realities. Take a breath and rest inside that picture for a moment, because it is a genuinely peaceful one. All around you, right now, in the dark of your room, this process, if the theory is true, is running silently at every scale. Stray molecules in the air drift into tiny superpositions, and, gathering mass and separation, are gently pressed by gravity back into definiteness. Countless times each second, everywhere, in your ceiling, in the sea, in the core of the planet, in the atmospheres of worlds no one will ever see. No observers required. The universe keeps itself definite the way it keeps itself round, by gravity, patiently, without supervision. Wigner's lifeless planet, the thought experiment that killed consciousness causes collapse, is on this account no puzzle at all. Its weather collapsed itself, storm by storm, for billions of years, minds or no minds, because clouds are heavy. The dangerous question's first half, how does the world become definite, would be answered, and answered with the least mystical ingredient in all of physics. But you have not forgotten, and neither has Penrose, that our night is not about cups. It is about the thing reading the cup. And here, the proposal takes its final, vertiginous step, the step that carries us back at last to Godel and the lecture room. Recall the audit. Collapse was the one process in physics stamped not computable, the one candidate source for whatever it is in the brain that outruns every rulebook. And now collapse has a mechanism, gravitational, objective, universal, with a calculable clock. So follow the logic where it insists on going. If understanding requires non-computable physics, and the only non-computable physics is gravitational collapse, then somewhere in the warm, wet, electric tissue of the brain, some structure must be exploiting this process. Something in there must be preparing delicate quantum superpositions, shielding them from the noise of the body long enough to matter, letting them grow to the threshold where gravity itself, not the environment, chooses the outcome, and harvesting those choices into thought. On the face of it, that sounds not just speculative, but biologically absurd. The brain is warm, the brain is wet, the brain is a thunderstorm of interference, the least likely quantum laboratory imaginable. Penrose knew this perfectly well, and when he published the idea in 1989, in a book that became, to everyone's astonishment including his own, a bestseller, he could not point to any structure in the brain remotely fit for the job. He confessed as much, with an honesty that still disarms, and we will hear that confession in his own words shortly. The mechanism half of his theory was an empty chair at a set table, and then a letter arrived from a hospital operating room in Arizona, from a man who spent his working days doing something no physicist ever does, switching consciousness off and back on for a living. What was in that letter is where we go next. The Emperor's New Mind was published in 1989, and nothing about its reception went the way books like it are supposed to go. It was 450 pages of Turing machines, phase spaces, relativity, quantum mechanics, and Godel, written by an Oxford mathematician with no gift for dumbing down and no intention of acquiring one. And it became an international bestseller, won the Science Book Prize the following year, and sat on nightstands around the world beside novels. Somehow its argument that the mind is not a computer, that something inconsciously awaits a physics we do not yet have, had found an enormous audience of people who had quietly suspected as much and were relieved to hear it from someone with theorems to his name. The professionals were far less relieved. Philosophers of mind and artificial intelligence researchers received the book roughly the way cartographers would receive a bestseller claiming the coastlines were wrong. The responses were fierce, brilliant, occasionally contemptuous, and they went on for years. Penrose had, in one stroke, reopened the dangerous question at maximum volume, under his own name, with his full reputation staked, exactly what the silence had been constructed to prevent. But the book's most consequential weakness was one Penrose confessed himself, and his confession, given late in life, is one of the most quietly moving things a great scientist has said about his own work. He had argued that consciousness requires non-computable physics, and located the only candidate in collapse. What he could not say was where, in the actual meat of the brain, such delicate quantum processes could possibly live. He went looking. I learned a bit of neurophysiology, he recalled, thinking that if I learned enough, I would find out what it is. He studied how nerves fire, the celebrated Hodgkin-Huxley description of the electrical impulse, hoping to find his opening. He did not find it. Nerve signals are far too large, too hot, too classical, and so the book ended the only way an honest book could. I just sort of tapered off at the end, he admitted, with something I didn't really believe, and that was the end of the book. Sit with that for a second, because it deserves the weight. The most controversial scientific bestseller of its decade closes with its own author, by his private admission, not believing his final chapter. He had built a door frame with no door, and in the way of these things, the door was at that moment driving to work in Tucson, Arizona, wearing surgical scrubs. Stuart Hameroff was an anesthesiologist, a working physician whose profession is, when you stop to look at it, the strangest standing experiment on consciousness ever run. Several times a day, every day, in operating rooms on every continent, anesthesiologists administer a small family of rather simple molecules, and a mind goes out. Not asleep, out. No dreams, no time, no self. And then, on schedule, they withdraw the molecules, and the mind comes back, intact, with its memories and its personality and its half-finished worries, as if reassembled from nowhere. General anesthesia is performed hundreds of thousands of times every day on Earth, and it has been in routine use since the 1840s. The first public demonstration took place in Boston in October of 1846, in a surgical amphitheater, remembered ever since as the Ether Dome, when a dentist named William Morton put a patient under with ether vapor, and a surgeon removed a tumor from the man's neck while he lay silent. When the patient woke and reported he had felt nothing, the surgeon turned to the gallery and said, "Gentlemen, this is no humbug. It was, by any humane measure, one of the greatest gifts medicine has ever given. Every surgery you, or anyone you love, has slept through descends from that afternoon. And here is the fact that should keep more people awake at night than it does. There is still no consensus mechanism for how it works. We know the gases are astonishingly selective. They abolish consciousness at concentrations that leave most of the brain's housekeeping running, the heart regulated, reflexes intact, neurons still firing. Whatever consciousness is, anesthetics find it with a precision our theories cannot match, reach past almost everything else, and turn off exactly it." Hameroff had spent his career fascinated by one particular hypothesis about where they reach. His candidate was not the synapse, the connection between neurons where mainstream neuroscience houses nearly everything. His candidate was smaller, stranger, and until then almost nobody's, a piece of cellular machinery called the microtubule. Microtubules are the skeleton of the cell, and calling them a skeleton undersells them badly. They are hollow cylinders of protein, about 25 millionths of a millimeter across, self-assembling from subunits called tubulin, 13 columns of them, arranged around the hollow core in a lattice of almost crystalline regularity. Every cell in your body is scaffolded by them. They haul cargo, they organize cell division, and neurons are packed with them, rank upon rank, running the length of every axon and dendrite. What seized Hameroff's imagination, and had seized it years before he ever heard of Penrose, was their architecture. The tubulin lattice looked, to him, less like scaffolding than like circuitry, a repeating grid of proteins, each able to flex between shapes, packed at densities that made the brain's synaptic wiring look coarse. A single neuron contains microtubule lattice enough to dwarf, in raw switching elements, the neuron's own synaptic connections. And anesthetic gases, intriguingly, are known to bind to proteins in ways that could plausibly reach this machinery. Hameroff's suspicion, nursed through the 70s and 80s at the far margin of respectability, was that the microtubule was where the real computation of consciousness happened, the fine grain beneath the neuron's crude clicking. What he lacked was a physics. Then he read The Emperor's New Mind, a book by a famous mathematician, arguing that consciousness required an exotic quantum process with nowhere to live, and he recognized, with the shock of a man finding his own missing puzzle piece in a stranger's book, that he had spent 20 years studying the housing. He wrote to Penrose. They met in Oxford, the knighted geometer and the Arizona gas passer, as anesthesiologists cheerfully call themselves. And out of that improbable meeting came the theory published in the mid-1990s under the name Orchestrated Objective Reduction, OR for short. The proposal assembled from both halves. Inside the microtubule lattice, quantum superpositions form among the tubulin proteins, shielded, they argued, by the lattice's geometry and by special conditions in the cellular water, from the brain's heat and noise. The superpositions grow, tubulin by tubulin, until their accumulated mass separation reaches the gravitational threshold, the Diosi-Penrose line we calculated in the last chapter, and then they collapse, objectively, non-computably, by gravity's own clock. Each collapse is, in their phrase, a moment of proto-experience, a raw flicker of awareness, and the neuron's own machinery orchestrates these events, hence the name, into the flowing cascade that is a conscious moment. Consciousness, on this theory, is not computation at all. It is a rhythm of gravitational choices, millions per second, sequenced by biology, and the brain is not a computer, but an instrument built by evolution to play the one non-computable string in the laws of physics. Their timing, whatever you make of their theory, was historically perfect, because the Great Silence was just then beginning to crack. In 1990, Francis Crick, who had already changed biology once as co-discoverer of the structure of DNA, published a paper with the neuroscientist Christoph Koch, arguing, in effect, that consciousness had served its sentence, that the word could be spoken in laboratories again, that the search for its neural correlates was legitimate, fundable science. Coming from Crick, whose credentials were beyond all suspicion, the permission mattered enormously. Within a few years, the philosopher David Chalmers had given the old difficulty its modern name, the hard problem, the question of why physical processing is accompanied by experience at all. And in 1994, the University of Arizona hosted the first of the great Tucson conferences on the science of consciousness, a raucous, brilliant, carnival-like gathering of neuroscientists, philosophers, physicists, and assorted heretics that became the homeless question's first fixed address in half a century. One of the conference's principal organizers, as it happens, was Stuart Hameroff. The exiled question was coming home, and the anesthesiologist from Tucson had helped build its house, none of which, let us be clear, made his theory right. It only meant that, for the first time since Wigner, a theory like his could be argued about in daylight. The scientific establishment's response to or itself, though, can be fairly summarized in one word: no. And the most quotable version of the no arrived in 2000, from the physicist Max Tegmark, who did exactly what physicists are supposed to do to a bold hypothesis. He calculated. Quantum superpositions, remember, are murdered by environmental noise, and the brain is a warm, salty, crowded swamp. Tegmark computed how long a superposition could survive in neural tissue before decoherence destroyed it, and his answers were annihilating. For the relevant scales, he found survival times in the range of 10 trillionths of a trillionth of a second, up to about a tenth of a trillionth of a second. The fastest things the brain does, by contrast, unfold over thousandths of a second. Between the quantum lifetime and the biological clock yawned a gap of 10 orders of magnitude or more, a factor of 10 billion. Proposing that the brain computes with quantum superpositions, the calculation implied, was like proposing to run a library inside a bonfire. The books burn 10 billion times faster than anyone can read them. For most of the field, that settled it. OR went onto the same shelf as Wigner's essay, the shelf of what happens to even the best minds. Hameroff and colleagues fought back, disputing the assumptions, arguing the lattice geometry, and ordered water change the arithmetic, pointing to newer, contested laboratory hints, delicate resonances in microtubules, anesthetics, interacting with them in suggestive ways, that the fire might have quieter corners than Tegmark assumed. The dispute has never been resolved to anyone's satisfaction. Honest scoring, tonight as always. OR remains a minority position, wounded but alive, its biology unproven, its critics unrefuted, and there matters would sleep, except for one thing. Half of the theory does not live in the brain at all. Half of it lives in physics, in that clean, calculable claim about gravity collapsing superpositions on a definite schedule, and claims like that have a property no theory of consciousness ever had before. You can build an experiment and ask the universe directly. In the 2010s, in the quietest place in Europe, somebody did. Under a mountain, we go next. In the mountains east of Rome, beneath the highest peak of the Apennines, runs a highway tunnel 10 kilometers long, and halfway through it, behind ordinary-looking service doors, opens one of the most extraordinary rooms human beings have ever built. The Gran Sasso National Laboratory is the largest underground research facility in the world. 3 enormous experimental halls carved into the living rock, with roughly 1,400 meters of mountain standing overhead. All that stone is the point. The surface of the Earth is a blizzard of radiation, cosmic rays sleeting down from space. thousands of particles passing through your body every second of your life, harmlessly, but loudly, if what you are trying to do is listen for the faintest signals in nature. 1,400 meters of dolomite rock hushes the cosmic blizzard almost completely, cutting the particle rain by a factor of about 1,000,000. Physicists go to Gran Sasso for the same reason monks once went to the desert. It is where the silence is. Come down into it for a moment. The elevator of the descent is a slow drive through the tunnel, fluorescent lights strobing past, and then the doors, and then halls the size of cathedrals, cool and dim, with the strange acoustic softness of places that rock has sealed away from weather. It is said to be among the quietest radiation environments on Earth, and the experiments squatting in the halls are shrines to that quiet. Tanks and cylinders swaddled in lead and copper and water shielding, listening, some of them for years on end, for dark matter, for rare decays, for neutrinos from the hearts of stars. In one modest corner of this kingdom of silence, in the late 2010s, a small team of physicists, Sandro Donardi, Cristian Piscicchia, Catalina Curcianu, and their colleagues, set up an experiment of almost embarrassing simplicity by the standards of the place. A small, exquisitely pure crystal of germanium, cooled and shielded from every source of disturbance human ingenuity could exclude, wired to record the gentlest whispers of radiation from within itself, wrapped in the most complete quiet available on this planet. And what they were listening for, patiently, month after month, was the sound of reality collapsing. If the Diosi-Penrose mechanism runs the world, if gravity is truly the executioner of superpositions, then the executioner should leave fingerprints. Here is the fingerprint, and the logic is beautiful enough to deserve a slow telling. Every charged particle in every atom on the Diosi-Penrose picture is ceaselessly drifting into tiny superpositions of position, and ceaselessly being collapsed back to definiteness by gravity, over and over, forever. But collapse, in the standard mathematics of these models, is not a perfectly gentle act. Each collapse gives the particle a minute, random kick, a tremor, as if the universe, in choosing where the particle is, jostles it slightly in the choosing. And jostled charges radiate. It is one of the oldest laws in the book. Shaken charge sheds light. So matter itself, every gram of it, should glow, incredibly faintly, with a signature X-ray whisper, the exhaust of reality being continuously decided. The whisper would be fantastically dim, but the model, in its simplest and most honest form, the form with no adjustable knobs, no free parameters to hide behind, predicts its exact loudness. A lump of germanium of such and such a mass should emit so many spontaneous X-ray photons per month, full stop. That is what makes the parameter-free Diosi-Penrose model a rarity among ideas about consciousness and collapse, and let us say this with the respect it deserves. It is a theory brave enough to name the number on which it will live or die. The team ran the vigil for months, gathered their data, published the analysis in 2020 and 2021 in one of the field's premier journals, and the mountain delivered its verdict. Silence. No excess whisper. The germanium sat in the dark under the Apennines, and did not glow at the predicted loudness. Not at it, not near it. The parameter-free Diosi-Penrose model, the cleanest version of gravity collapses the wave function, is dead. The universe was asked, directly, and the universe said no. Now, if this were a tidy story, that would be the ending, the dangerous question laid to rest at last by 1,400 meters of Italian rock. But you have been with me all night, and you know by now that nothing about this question has ever been tidy. Because listen to Penrose's response from that late interview when the experiment under the mountain came up. Some people say this disproves the Penrose theory, he said. But it is not the Penrose theory. My scheme does not involve the heating. And this is not, as it might sound, a man moving the goalposts after the whistle. The record supports him. The kicks, the tremor, the glow, arise from a particular mathematical implementation of gravitational collapse, the one Diosi had formalized, with machinery Penrose had never adopted. Penrose's own version had always been vaguer about the collapse's fine mechanics, and, crucially, he had independent reasons, cosmic ones, for insisting the process must be gentle. If collapse heated matter, he pointed out, the universe would show it, and his favorite witness is one of the strangest objects in the sky. A neutron star is the collapsed core of a giant sun, a ball of matter the size of a city with the mass of a star, so dense that one spoonful outweighs a mountain range. Neutron stars are, in effect, single gargantuan atomic nuclei, matter at the maximum density nature permits outside a black hole, and on any collapse model with heating, all that fantastically compressed matter should be simmering with the exhaust of relentless quantum collapse, warming itself from within, measurably, forever. Astronomers know the thermal lives of neutron stars rather well. They cool quietly, on schedule, as ordinary physics says they should. No anomalous simmer. So for Penrose, the mountain's silence was not a refutation, but a confirmation of something he had already believed. Whatever gravity does to superpositions, it does without shaking them. The executioner has soft hands. You might think that lets him off easily, and so did some of his colleagues. But here is the part that tells you most about the man, and about the price of honesty at the edge of knowledge. Making collapse gentle, it turns out, is mathematically brutal. Remove the heating from these models, and you break, of all things, their relationship with time. The mathematics that avoids the tremor requires the collapse process to reach, in a certain precise sense, backwards, for the theory's account of the present to depend partly on what the collapse will have settled, as though the choosing of reality were smeared across time, rather than pinned to an instant, as though the cause, in Penrose's own uneasy phrase, goes back into the past. Now, a lifetime of physics screams at this, and Penrose knows it better than anyone alive, so hear how carefully he threads the needle. Nothing in his scheme lets anyone send a message backwards. No signal, no paradox, no changing what has been observed. The retro reach lives entirely within quantum reality, the shy, blank-faced, unanswerable kind of being we met with the electron, the kind Einstein's criterion certifies as real, but which never holds a press conference. Only quantum reality bends backwards, and quantum reality, by its nature, can never be caught doing it, never used to cheat causality, never made to carry news. Classical reality, the cup's kind, the kind your memories and your mornings are made of, stays rigidly ordered, past before future, cause before effect, always. Two kinds of reality, one of them slightly loose in time, and the looseness is exactly what lets gravity choose the world's facts without leaving fingerprints. He has written this picture into his later books, and he is still, in his 10th decade, trying to sharpen it, and he says so with a workman's plainness. It is in the book, he said, but perhaps it needs a little bit more sharpening up. So step back and look at the strange scoreboard the mountain left us. One theory, the parameter-free Diosi-Penrose model, is genuinely dead, killed exactly the way science is supposed to kill things, by a number and a detector. Its co-author, Penrose, survives, but wounded into strangeness. His surviving version, alive only at the cost of a picture of time that even he calls unfinished. The mainstream keeps decoherence, keeps the unsolved problem of outcomes locked in the basement, and keeps not asking. And the question itself, the one the founders asked openly, the one Wigner spent, the one Penrose staked his legacy on, walks out from under 1,400 meters of rock entirely unharmed. Because notice, and this is the last hard thought of the night before we come home, the experiment tested collapse. It could not, and no experiment yet conceived can, test the connection between collapse and the thing you are doing right now, this warm, dim, first-person listening. That connection remains what it has been since the beginning, an argument, a hunch, a signpost in fog, which returns us, at last, with everything we have gathered, to the question we set out with, while the kettle of the night was still warm. Why did physics stop asking? We have all the strands in hand now. It is time to braid them, and to hear, in his own words, what the asking cost the one man who never stopped. At the beginning of tonight, I made you a promise. I said that by the end, you would know exactly why physics stopped asking the most dangerous question it owns. You have felt the answer gathering all night, strand by strand, and now, in the quiet at the end, we can finally braid it, plainly, the way you would explain it to a friend in a dark kitchen at 2 in the morning. Physics stopped asking, first, because it could not answer. That is the most honorable strand, and it deserves to be said first. Science runs on questions that can be broken into pieces small enough to test, and for most of a century, the consciousness question offered no purchase at all. No number, no detector, no wedge for the experimental knife. The founders asked it and could not advance it. Their students, watching, drew the practical lesson. A question that cannot be worked on is not, whatever else it may be, a day job. Physics stopped asking, second, because the money and the mood changed. The war remade a small philosophical guild into an immense technical industry, and the industry's virtues, speed, precision, production, had no line item for wondering what an observer is. Shut up and calculate was never a rule. It was a paycheck, a culture, a raised eyebrow, and cultures discipline more efficiently than rules ever could. Third, because the neighbors were worse. The question's respectable custodians abandoned it, just as its disreputable ones adopted it. And for a working physicist, the mere vocabulary of the subject came to smell of séance smoke and sales conventions. No one wants to share a shelf with the boutique. The cranks did not merely embarrass the question, they made caution look like integrity. Fourth, because decoherence gave permission, the one technical embarrassment that kept the question alive, the naked seam in quantum mechanics, was dressed so expertly by the mathematics of environmental noise that a physicist could spend an entire career without ever seeing what the dressing covered. The surviving problem of outcomes, still unsolved tonight, still waiting in the basement of the theory, patient as ever. And fifth, the quietest reason, and the truest, because the question is genuinely dangerous, in the way we named at the very start. It sits at the junction of the two things we most need to be true of ourselves and our science, and whichever way it resolves, something enormous falls. If mind is computation, we lose a certain irreplaceable specialness, the conviction that understanding is more than machinery. If mind is not computation, we lose the completeness of the scientific picture that 4 centuries of triumph had seemed to promise. And physics itself must someday be rebuilt around a process it currently files under randomness. Institutions do not walk toward that kind of stakes. They wait, and they let the brave go first, and they watch what happens to them from a safe distance. You have seen what happens to them. Wigner, the politest man in physics, asked at the height of his powers, and spent his remaining decades softly reclassifying his answer as play. And Penrose asked, with more mathematics and more stubbornness than anyone before or since, and it is his accounting of the cost, given in his 10th decade, that I want to leave with you, because there is nothing else like it in the literature of science. An interviewer asked him, late in life, what he was most misunderstood about, and he did not name black holes, or the geometry that carries his name, or any of the mainstream glories no colleague has ever disputed. He named this. The consciousness thing, probably, he said. The trouble is, that is a murky subject. And then, the sentence that has been waiting for us all night. Probably I am not sure I should have got into it at all. Feel the weight of that. A Nobel laureate, one of the great scientific minds of his century, looking back across 60 years at the most famous idea he ever had, the best-selling books, the theory with his name on it, the experiment under the mountain, and wondering aloud, mildly, without self-pity, whether the whole excursion was a mistake. There is a lifetime of raised eyebrows in that sentence, a lifetime of being introduced with a slight apologetic pause, the brilliant Roger Penrose, who also, well, has this other interest. That is what the most dangerous question in physics does to the people who ask it best. And then he finished the thought. It is a good question, he said. I think I am glad I did. I am glad he did too. Not because his answer is right. Tonight has been scrupulous on that point. And I will be scrupulous once more, here at the end, where honesty matters most, because you are nearly asleep and inclined to believe me. His answer is probably not right, if the history of bold first answers is any guide. The Godel argument stands unresolved after 60 years of siege, a standoff, not a victory. Or is a wounded minority position whose biology remains unproven. The gravitational collapse mechanism, in its cleanest form, is dead under an Italian mountain, and in its surviving form is a picture, even its author says, needs sharpening. Every single plank of the edifice is contested, and the mainstream, with its decoherence and its patience, may simply be correct that mind is computation all the way down, extraordinary, but not exceptional. That is a real possibility, and nothing in tonight's story rules it out. But here is what the story does establish. Beyond any of its particular claims, the question was never answered. It was abandoned, managed, exiled, priced out of careers, laughed into the boutique, dressed over by good mathematics, everything except answered. The fish never did see the water, and the water is still here. It is here, in the operating rooms, where consciousness is switched off hundreds of thousands of times a day by molecules we do not understand. It is here, in the basement of quantum mechanics, where the problem of outcomes sits exactly where von Neumann left it in 1932. And it is here, suddenly, urgently, in the machines, because we have now built devices whose cleverness is beginning to rival our own, and the question of whether cleverness is understanding, whether anything is home in there, has stopped being a lecture room curiosity and started being a question civilizations may need to answer correctly. The exile is ending, not because physics grew brave, but because the world grew machines. The dangerous question is coming back to the table, and it is bringing consequences with it. So let the story rest now, and let me gather its images for you one last time, loosely, the way you gather things at the end of an evening. Hold the sentence from the Cambridge blackboard, the little arithmetic prisoner that says, I am not provable by these rules, true and unreachable, the crack in every rulebook. It has one more thing to give us, here at the very end, because you, listening in the dark, are something the laws of physics can describe, particle by particle, field by field, and the experience you are having right now, the dim, warm fact of being someone, is a truth those rules have never once derived. You are, as far as anyone can honestly say tonight, the Godel sentence of physics, written in its language, undeniably true, and not yet provable from anything it knows. And hold the cup. Hello, cup. What is your shape? The universe, it turns out, is furnished almost entirely with things that answer. Moons and molecules and cups, patiently holding their press conferences for nobody. And it contains, as far as we know for certain, exactly one kind of thing that asks. Physics has spent 400 years mastering the answerers. It has not yet begun on the asker. Perhaps that is not a scandal. Perhaps it is just the order of the work, the way you sweep a house from the front door inward, and the innermost room simply waits its turn. The universe kept itself definite for billions of years before anyone was here to ask it questions, gravity, or something, patiently closing every blur into fact, world after world, storm after storm, and then at some point, on at least one small planet, some of those facts arrange themselves into a shape that could wonder what facts are. Whatever the mechanism turns out to be, computation or collapse or something no one has imagined, that arrangement happened, and you are it. And nothing in tonight's long story of silences and mountains makes that one datum less astonishing. The most dangerous question in physics is lying right behind your closed eyes, where it has been all along, and it can wait until morning. It has waited 100 years. Thank you for spending this night with me, walking the whole length of it, from the chalk dust of Brussels to the quiet under the mountain. If explorations like this one are how you like to end your days, a like or a subscribe would mean a great deal to me. It is a small thing for you, and it genuinely helps me keep making these long walks through the edges of what we know. And remember, the next time you pick up a cup, warm in your hand, definite as anything in this world, that the cup answers every question, and you are the reason there are questions. Good night, and may you never look at your own thoughts the same way again.